Hello, hello. Oh, okay, new avatar. Hello. Afternoon. Yes, good afternoon, Eric. Thank you for hi. Okay, I'm gonna do the chat. Good afternoon, Eric. Thank you for clarifying about today's class. I appreciate it. Good afternoon, Alexis. Oh, hello, Claudia in the 3D. Hello, Paulina in 3D. Well, 2D. Anyway, in animation. Hello, Maria in live and in person. Hello, Stephanie and Eric and Katie and Shy and Alexis. Thank you for having imagery. Wait, who else? Okay. I'm going back and forth. Hi, Victoria. Good afternoon, Shy. Good afternoon, Katie. Wait, more people coming.
Good afternoon.
Oh, who just said, oh, wow. Was that Shawnee? Oh, good afternoon, Shawnee. Thank you for saying so. And I hope you got that email from me. We could talk about it right after class or another time. But if you, I sent you an email last week. Anyway, okay. Good afternoon, Stephanie. Good
Yeah, I
afternoon.
didn't have access last week. They just fixed my Blackboard in my email.
Your black. Okay. I don't think it was to black, but okay.
No, they just fixed both of them because they're linked in my case.
Oh, I see. Okay. Gotcha. Okay. Thank you. Okay. Good afternoon. Wait, so I said Stephanie. Good afternoon, Stephanie. Good afternoon, Maria, twice chatting and videoing. Thank you. Good afternoon, Brandon. Good afternoon, direct chat person. Oh, and also direct chat. Wait, reading direct chat things. Gotcha. Okay, bearing with. Yes, got you. Thank you. Good. Yeah. Oh, okay. Now Claudia's question. Okay. And as usual, I love Claudia's questions. I love anybody who's asking me specifically what they need in the class. But wait. Not sure. Okay, hold on. More people coming. About Claudia's question about question 7. I mean, about homework 7. What? Okay, hold on. I'm reading a bunch of direct chats. I'll just quickly say, because I do want to get to it. Of course, I love Claudia's question. And in fact, I understand. Or sorry, wait, was there a public question? I'm sorry. Wait a minute. Yeah. Oh, it was a public question. Okay. Yeah. I even know very specifically what she's asking, and it's like a big thing that we are definitely going to talk about, like whether Claudia asked it or not. But as usual, she's like ahead of me in a good way. I can tell you right now, we're not going to get to it today because we're still, you're not going to get new homework tonight. Homework 7 was due because yes, you're supposed to try it and work on it before I start going over it. But we're still going over 6 today, which is something also I think Claudia had wanted to see last week. So you guys are ahead of me right now, and that's as it should be. That's good. I will. I totally respect and appreciate the question in particular about homework 7. And we will get to it, but we won't get to it today. Just so you know, okay. And I'm like looking at and let me know if that's too confusing or annoying, or we could start talking in private about it. But wait, okay, I'm looking. Got it. I see the direct chat. Oh, hello, Josephine. Good afternoon, Jenna. Okay, we're gonna start in a second. Let me just hold on. Let me just respond to one thing. We will start in a second. Okay. Okay. I'm responding to a couple of direct chats. We will get started in a second. Again, we're going to go back to homework 6 today for good or for bad. You're not going to get a new assignment for a little while because but you know, it's definitely at that point in the year already where people are starting to fall behind, and I understand that. So when you don't have a new assignment, definitely use it to catch up. Remember, every portal is still open. Hold on a second. Every portal is still open, so anything you haven't done can still be handed in or updated or revised, et cetera, et cetera. At all times, what is due for each of you individually is whatever the next thing is that you're up to. Like, I don't mean that sarcastically. Like, if you've only done 2 homeworks, then what you need to do is homework 3, et cetera, et cetera. You just go in order, just like I'm going order in class, and some of you are ahead of me and some of you are behind me, but you just go in order. Okay, that's about okay. I'm just trying to respond to some things in the direct chat. We're going to start in this okay, wait. Oh, great. Okay. And again, things are happening in the direct chat. I apologize. I do want to get going. And I'm going to say too, before I forget, in a minute, we're going to turn our attention back to homework 6. We're in the middle of going over homework 6 right now. Generally speaking, I stay right after class to answer questions that anybody might have. Generally speaking, I try to do that, but today I can't do that because today is as you know, it's a Monday schedule, but it's a Tuesday and the whole world doesn't think it's Monday. So I have to rush right after this class. And just also to remind you, I try to answer questions right after class, but I can't do that today. But if you ever want to see me in office hours, the best time, if you want to see me in person, the best time is office hours, which is generally 11 to 1 on Tuesdays. Like I am in my office right now at John Jay, but because it's technically Monday, that's all a little bit confusing today. Anyway, I definitely don't want to leave anybody hanging with questions. Today I won't be able to, so please text or email me right after class or at okay, I'm just looking through it. But so I'm looking at the direct chat. Hopefully I answered all the direct chats. And again, I appreciate that all of you are staying alert to the alerts. Like, technically this is a, what do they call it? Mixed online synchronous and asynchronous. So sometimes as you've been very good about, all of you, sometimes we do class like this, live like this on Zoom. But sometimes the other section does it live on Zoom, and then we tape that section, and then you watch the video. And you guys have been very good about responding to the communications and doing that. That will continue to happen, like alternate, not literally every week, but often. But I think you're getting it. And if there's any confusion about that, email me. Okay, so today's one of those days. Like you're here now, that's great. But if you have friends in the other section or whatever, hopefully it's clear to them. They're going to watch. They are not going to meet today because it's Tuesday, but it's Monday, but they will watch your video. Okay. Hold on 1 second. There's more happening. Okay. Okay. So what is that? Oh, but then there was a question in public chat I want to answer. Yes, very good question, Shy. And I'm saying Shy, I think that's what you told me to call you. If I'm making that up and you didn't tell me to call you that, please forgive me and I'll take it back. I think you told me that. Anyway, yes, you guys, you can type out your homework. You can. That's a very good question. In fact, especially those of you who you can. I'm not saying you have to. And in fact, in most cases, I think the easier thing for most of us is to write out our homework and then scan it in and create a PDF, like 1 file per submission, please, 1 file per submission. But you absolutely can type it. Those of you who know how to use LaTeX or like math typing type translators or compilers, like that's fantastic. beautiful. The only thing about typing it, I just want to, remind you or underscore, if you can think that way, if you can type like mathematical, scientific things, terrific. I'm all for it. But please, nonetheless, you have to find a way to integrate diagrams in, right? Like as long as it includes diagrams. And one thing I'm noticing, like, yes, more and more people these days are typing, which is terrific. But whenever you get, all of you, it's a very legitimate question. Whenever you get to the algebraic or calculus mathematical manipulation piece of a physics problem, really the part that we call step 4, particular application and work, when you get to step 4 of a physics problem and you're manipulating equations and plugging things in, etc., there you have to be careful, especially if you're typing. The sort of the expectation there, the expectation set by journals and publications and so forth, is that each new line of math, each new equation would be on its own line and would be centered, right? I mean, that's sort of important. I mean, all these things are more important than they sound. It took me a really long time to adjust to the fact that formatting standards are far more important than I ever wanted to believe. I promise you. But so when you do the math, each equation should go on its own line and should be centered, and you show what you're doing to the equations as you go. Ideally, you have each bit of math centered on its own line, and off to the side or something, you have commentary in English of what's happening, or you can put the English commentary interspersed line by line. But definitely don't just want, if you're typing, any and all of you, you don't want just thick, dense blocks of text or of math, like where we follow it from left to right and left to right. Like that is too hard on anybody to follow. So, and it's not the tradition. So but I think you understand what I'm saying. But yeah, if you can type, all the power to you. That's terrific. Okay, I think I'm. Okay, great. And thank you, Shai, and submit that for points for closing the loop. Okay, so we're going to go back if there are any questions, of course, stop me. But I think what we're going to do now is turn our attention back to homework 6 we were in the middle of. Yes, okay. So we were in the middle of homework 6. The top equation here on the board right now is, as I hope you're starting to know, the top equation on the board is Galileo's principle of relativity, form number 4. It's the 4th form of that principle of relativity. It's the first time the principle of relativity starts becoming, and it's case 3 of form 4, I should say. It's the first time the principle of relativity, the idea that all velocities are relations between pairs of objects rather than properties of single objects. This idea, and it is an idea, I mean, it's a truth, but this fundamental principle upon which all the laws of physics are built, this principle, super important, super simple in a way, but super hard to get one's mind around in another way. It starts becoming mathematical with this expression right here, which we developed in the last couple of classes. And I want to say that many of you, in your responses to the video of that class, I was really, really impressed and really happy that so many of you wrote about one thing that you understood or took away from it, as I asked you to do, and you wrote one thing you still needed help on, as I asked you to do. And I'm really happy that people took this so seriously, because many people in your class, when they saw the video that brought us to this equation, what many people said was that they understood, or they felt they understood, case 1 and case 2. They either already sort of believed them, already knew them, or they became clear with the video game examples. Like, many people said that, which is terrific. But then many of you said that this piece sort of kind of maybe made sense, but that you really wanted to see concrete examples of how this plays out, or you really were unsure, many of you said, of like how you would actually use this in problem solving. Great question. Totally fair. Totally glad to see that you recognize that. So that's what we're going to start seeing today. I want to say right now, like I'm going to, it's going to come up, and it really, it comes up today in one example we're going to do in homework 6. But then homework 7, just so you know, if you're just starting to struggle with it or whatever right now, homework 7 is all about, or ultimately all about this. It's particularly about how this gets expanded to 2 dimensions. So absolutely, you're right to say you don't get something until you start seeing concrete examples. Homework 7 is all the concrete expansion of this. But right now, let me turn to homework 6 and show you like one case where this works. And I'll, before I forget, the equation underneath it is the one that gets derived later in homework 6. So that's the new thing. We haven't technically gotten that equation yet. That is what we derive in one of the problems in homework 6. So let me turn now to homework 6. I'll tell you what question I think we're on. Whoa, hello. Losing my screen. We're going to homework 6. Oh, here it is. Okay. And I want to go in homework 6. I'm not going to switch the screens. Hopefully you have it in front of you. Homework 6 called Big Old Duck. I'm going to go straight to problem 3E. Bear with me for a second. So, okay. Homework. Oh, homework 6. Problem 3E. So this is all the business of the bolt A and bolt B. And I'll just remind you of the fact, well, okay, really quickly. Just to remind you of the fact, bolt A was dropped at 0 meters per second at time equals 0. Bolt B was dropped at 40 meters per second at time equals 5. Those were the facts, right? Okay. And the question here for E, the question is, draw a VT graph from T equals 0 to T equals 10 from the reference frame or the perspective of, so it's a VT graph, of bolt A, from the, or in the reference frame of, or according to bolt B. This is the question, okay? I'm going to pause for a second because something just said, so that's what I'm going to answer right now. But let me warn you, or let me say, this right here will be a concrete example, maybe example number 1, of Galileo's principle of relativity, form number 4, case number 3. Okay, the thing that people were asking about, this is it right here. But bear with me for a second. I'm sorry, 85 things. This whole Monday, Tuesday thing really makes me even more spazzy than I already am. Just bear with me. Okay, bear with me for a second. Or maybe what I would suggest, I'm saying bear with me. What I would suggest is, even if you've already done the homework, or I hope you have, maybe set your homework aside for a second, and for your own sake, for practice, try to make this graph right now, whether you've done it already, whether you think you're correct or not. I mean, I think most of the homeworks have been corrected, but try right now, thinking of it in terms of VAC equals VAB plus VBC. See if you can relate, if you can see how this question is related to GPR. And I'll say this, don't get bogged down in the fact that it's a graph. If you don't like graphs, that's one thing. Okay, we could talk about graphs, but I am not trying to suggest that GPR, that Galileo's principle of relativity, like always necessarily is about graphs. Not at all. So if you want, like, ignore the graph aspect for a moment and just think about what the question is asking and see if you can see how it's related to Galileo's principle of relativity, form number 4. So bear with me. So think about that. Maybe try to make the graph right now and give me a second. Sorry, and someone else is coming in. One second. Okay, sorry. Okay, so let's see what just happened. Someone else is here. Okay, so here's what I'm saying. With the bolts. I mean, and if anybody wants, well, I'll just say what I'm saying because I'm being so spazzy. So it is asking here. We are asking before I even get to the graph. Okay, this question is asking. We are being asked to consider V of bolt A according to bolt B, right? We like according to, that's the same thing as relative to. That's the same thing as like I'm saying these are all synonyms, and you really might want to make a note of this. If this, and some people were asking me about this, some people said and again, I'm very excited at how specific people are when they respond to these videos. Like it almost makes me feel like the videos are doing something. Like people were asking, like some people were saying that a couple of people said they sort of get the relative velocity thing, but they only get it when one of the velocities is 0. Does it also apply when neither of the velocities is 0? Or at least one person said that. And then one person said the exact opposite of that. Like literally, like people were saying, I'm not sure like how broadly this thing applies. I don't get it when there aren't zeros, or I don't get it when there are zeros. So great question. Here's the point. It applies across the board. We may have to practice it more, whether there's zero. It's easiest to picture when there's zeros in a way. But the whole point is that from here on in, this is the only way velocity works. So what am I getting at right now? What you might want to put in your notes are any of the following phrases are all of the following phrases are all synonymous. If I say velocity of A relative to B, or I say velocity of A compared to B, or I say velocity of A according to B, or if I say velocity of A as measured by B, or I say velocity of A in the frame of reference of B, or velocity of A in the reference frame of B, all of these mean the same thing. And what they ultimately mean is the velocity of A if we assume that B has a velocity of 0. Okay, this is where the zeros come in now. Obviously, I'm going to write this down in a second. But like the thing that is both easy and hard to get one's mind around is the video game idea. We're saying anybody not only can always view themselves as stationary, as having a velocity of 0, but as long as they're not speeding up or slowing down or turning, as long as someone's moving at a constant velocity, not only can they, but they almost must view, they must view themselves as stationary compared to themselves, right? Like that's case 1 of GPR form number 4. And that's what all of you who play video games or watch movies really do understand, right? Or any of you who lives in the world, when you walk through the world, or you drive through the world, or you take a subway through the world, if you think about how you visually experience the world, you don't visually experience yourself as moving through the world. You visually experience the world as moving past you, right? You view yourself as at rest. Like if you're always looking, if you hold your finger in front of your nose, or you have glasses that slip down your nose and you see your glasses are always right in front of your eyes, and they're always the same distance in front of your eyes, right? You don't move away from yourself. The thing, and everybody knows that. And I'm sure everybody has considered this in one way or another in their mind. The thing that I'm telling you that is actually harder to accept in a way than one might realize, I'm telling you, that's not that's not some trick or some game or some silly illusion that's fooling you. That is as correct as any other velocity you would ever ascribe to yourself. Like what I'm saying, I'll get back to the problem, but what I'm saying is, if you can visualize that you are at, if you can visualize how you are at rest, but trees are moving past you at 20 miles per hour to the east, right? Like say you're in a car or something that's traveling to the west past the trees. If you can visualize that to you, you are at rest, and to you, the trees are going past you at 20 miles an hour to the east. What I'm trying to tell you as a physicist is, don't then actually say to yourself, but actually the real truth of the matter actually is that the trees are sitting still at 0 and I'm going past them at 20 miles an hour to the west. What I'm here to say is, you could also view it that way, sure, and the trees might be viewing it that way, sure, but that is not the actual truth of the matter any more than your original perspective or reference frame was. The actual truth of the matter is that there is no actual truth of the matter, and I mean this dead seriously. This is not a philosophical point. This is a scientific point. What I'm saying is, you may be 20 miles an hour, you might be moving 20 miles an hour past the trees, and you might be 0 miles an hour compared to, let me say that again. You might be going 20 miles an hour relative to the trees, and you might be going 0 miles an hour relative to yourself, but you're also standing on a thing called Earth, which we all believe is going 65,000 miles per hour past the sun. And I might add that we all in modern day believe that the sun is going 650,000 miles an hour past the galactic center. What I'm trying to say is that there is no actual number that actually is describing you or planet Earth or the trees any better than any other number is actually describing. What I'm saying is that velocities only make sense as comparisons. I'm saying, and the way the comparison works, now to get back to this, okay, the way the comparison works is from here on in, there is no such thing as velocity of A, whatever object A is. There is velocity of A compared to B, and there is velocity of B compared to A, and each of them is as equally valid as the other. Velocities differ depending on what you compare them to, and you have to pick a standard of comparison for any given one problem, or what we call in physics a frame of reference. You have to pick a frame of reference, and what it means to solve a physics problem, and what it means to pick a frame of reference is to decide what object is being regarded as stationary. So, okay, so I'm going to, so in this problem here, whoops, sorry, in this, where's the page? Okay, in this problem here, when they're asking to, what's the velocity of bolt A according to bolt B, or they're asking for the velocity of bolt A relative to bolt B, all of that means the same thing as what is velocity of bolt A in the reference frame, I guess that's what it originally said, in the reference frame of bolt B, which really means, what I'm trying to say, what that really means, that means if we assume or regard bolt B to be at rest, stationary, if we're playing a video game from which bolt B is the first person, is the player, right? And again, I'm harping on the video games because a number of people actually said in the chat and said that the video game example works for them. So again, I know it alienates some people, but hopefully it's helping some. And again, it doesn't matter if it's a video game, it could be a movie. But if we regard bolt B to be at rest, that means if we assume or regard bolt B to be at rest, then what velocity do we measure or observe for bolt A? Okay, that's the question that's being asked. So all of that English means we're asking what is the velocity of VAB? Like the VAB and the two objects could have been called, MN or CD, like they could be called anything. But when I write VAB, what I mean is this. I mean the velocity of A relative to B. It means assuming that B is at rest. And really what I'm trying to say, if you're getting the point, is that something is always assumed to be at rest. When people are asking, like, does this work when there aren't zeros? I mean, yes, it all works when there aren't zeros, but kind of the point of this is we're always, to look at something from a perspective, is to assign the number 0 to something. Okay, so I'm belaboring the point. So here, so we want VAB. Now, how do we know VAB? Well, what is VAB? Okay, here's where GPR number 4, case 3 comes in. And again, I'm dragging it, like a lot of you might have gotten this graph in 1 second without all of this talk. And that's fine. And if you got it right, you got it right. But can you even see me? Okay. But what I'm trying to do here is link this question. I'm trying to show you, since so many people asked quite legitimately, I'm trying to show you how this GPR4 thing applies to physics problems. So if this problem is asking us to analyze a VAB, like, Okay. Now so I'm going to apply it. Okay. The fourth form says, the case 3 says VAC equals VAB plus VBC. Okay. Now A, B, and C can be any three objects, any three reference frames. It happens that in this problem, we are also using the initials AB, but this can be applied to any problem, even if you're not, even if. So here, what I mean is here by A, we mean bolt A. That's not, okay. Here, B equals bolt B. And what is C? Good question. What is C? Because the problem doesn't seem to ever mention a C. What C is in this case would be a third frame of reference, a frame of reference in which apparently both of the bolts had both the bolts' velocities were originally measured in terms of. In other words, here in this problem, C would be like planet Earth, or you could say the reference frame of the lab. Okay, now those are two different objects, planet Earth and lab, but you can call it either one you want. Earth and lab sound very different, right? I mean, Earth is like this big planet, and the lab is this like little room on the 3rd floor of John Jay. They sound like two totally different places, right? And they sound like two different sizes. They are two different places. They are two different objects, but they are the same. In this case, Earth and lab are two different names, or two different ways of describing. Sorry. Two different names for the same reference frame. Now, what do I mean by that? Again, I'm dragging this out to make a point, okay? You might have done the problem a lot quicker, but I'm trying to explain what I mean by the relative nature of velocities, and I'm trying to explain what I mean by reference frame, because it takes some getting used to. I am saying that the Earth reference frame or frame of reference is the same as the lab frame of reference. How could I say that even though they're two different locations? A reference frame is not a location. A reference frame is a perspective, and it's a perspective dictated by velocity. Not location. Here's what I mean. The lab at any given moment is moving the same velocity as planet Earth is. And again, until you get used to this idea, you might say, wait, what? The lab is moving at the same velocity as Earth is? The lab isn't moving at all. What I'm telling you is, yes, it is. Everything is moving. Nothing is objectively or actually or by itself stationary. That's the thing we have to get used to. Stationary is an assignment that we make to an object when we choose to view the world from the perspective of that object. Nothing is objectively or inherently or actually sitting still. Nothing has its own velocity. Planet Earth is still relative to itself. The lab is still relative to itself. But more importantly, the lab is stationary, is moving at 0 relative to Earth. The lab is stuck on Earth, right? Whether I'm looking at the universe from the perspective of Earth and saying the sun is going past the Earth at 65,000 miles an hour, Or I'm looking at the universe from the perspective of the sun and saying that the earth is moving past it at 65,000 miles an hour, each of which is a valid choice. Either way, I'm going to come up with the same speed every time for the lab as I do for the earth. Either they're both going 0 or they're both going 65,000 or whatever, because the lab is stuck to the earth. Right? I'm not like trying to trick you. I'm trying to emphasize the lab frame of reference. The way we look at the world from the lab is the same as the way we would look at the world from standing on the ground on Earth. It is not the same as how we would look at the world if we were in an airplane, like traveling past, or a car, or blah, 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 or Jupiter, or the sun, right? In other words, a frame of reference is how you look at the world, your perspective, your coordinate system on the world as dictated by your velocity. Whatever the velocity of Earth is the same as the labs. They are both still relative to each other. So they are the same frame of reference. If I'm standing in the lab, then my frame of reference is the same as the lab and as Earth. If I'm walking through the lab, I don't care that I'm in it. I could be literally in the lab, but if I'm walking through it, then I'm in a different frame of reference because because then I would see the lab as moving past me. Frame of reference is a perspective dictated by velocity. So to get back to the problem, I know I'm really, I don't know. To get back to the problem, I'm using letter C. Sorry, and I'm using letter C to stand for whichever you like, the lab frame of reference or the Earth frame of reference, whichever's more comfortable to you. I'm saying they're the same thing. So what do I do? So I go to the next page. So I'm going to say, okay, according to the principle, the velocity of bolt A relative to the lab equals the velocity of bolt A relative to bolt B plus the velocity of bolt B relative to the lab. That's what I'm saying. Now I guess I'm talking so much. I'll just stop, right? But what we are solving, we're being asked to solve for VAB. So what do I do? Like, how do you apply this principle to a particular problem? The principle says AC equals AB plus BC, but we're solving for AB. So I'm going to just do math, regular algebra. I'm going to subtract from both sides. I'm going to say, okay, VAB, so subtract from both sides. Subtract BC from both sides. I'm going to say VAB equals VAC minus VBC. I'm just doing algebra on the principle, right? What does that means? Example, if like at the example, right, at time equals 5 seconds, right? We were told that VAC means the velocity of the bolt relative to Earth or relative to the lab, wherever we were making these measurements from. So VAC at the beginning, right, at t equals 5 seconds, I believe the velocity, was 50 meters per second. Right? Yeah, because you figured that out above, and because it started from rest at time equals 0, and every second it gained 10 seconds. If you want me to review that, I can, but I believe we know that at t equals 5, VAC equals 50, and VBC, I believe, equaled 40, because it was given in the, and there's a question. Awesome. Let me just write this before I forget, but awesome. I'm psyched you have, I think you have a question, Josephine. Hold on one second. But I believe this was given. Hold on one second.
Yeah.
Oh, yeah. Okay, go. Yes, please.
The 50 meters per second, that is because it's been 5 seconds, and every 5 seconds it gains 10 meters per second. And is this in relationship, like, is this from the perspective of bolt A?
Wait, perfect. Oh my God, great question on every level. And please submit for points for this question. And thank you for using your voice. Okay, awesome question. And it's like a 2-part question. So first of all, yes, yes, yes. Many times, yes. The 50 I got from exactly what you just said. And I think we did it earlier in the problem. But yes, because at t equals 0, it had 0 velocity. And every second it gains 10 meters per second of velocity, like according to its acceleration. Yes. So totally yes, and I'm glad you're asking. But then the other thing is, I'm glad then Josephine threw in this. So what perspective is this from? So what we're this is a tricky point. What we're talking about is bolt A, but the perspective that we're talking about it from is the lab, or is planet Earth, if you like. Like the beginning of this whole problem is saying, on one fine instant, you see a bolt known as bolt A get dropped from rest down an infinitely deep rabbit hole. Okay, so I guess we're not in a lab. I guess we're in a garden. But like you see a bolt known as bolt A get dropped from rest. So in fact, let me go a step further. I'm so glad Josephine's asking this. When I say lab, or what I guess I should really say garden, I guess this is all happening in a garden, or I say planet Earth, another word I could use for all of that, for what I mean by lowercase c in this problem, is you. Like the problem says, you see a bolt. You see a bolt get dropped from rest, blah, 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 blah. So apparently you are standing in the lab watching all of this. So it's your perspective that we're talking about, your frame of reference. And what we can assume is that you are standing still in this garden, or in this laboratory, or in this planet, or on this ground of planet Earth. It's your perspective that originally got all of this data, all these facts from the original problem. So to answer, but I'm so glad Josephine's asking this. So what I'm saying, you are a third frame of reference. You are what I'm calling like lowercase c in this example. Bolt A is object A, bolt B is object B, you are perspective C. Now there's no rule that necessarily you all have different numbers, you might or might not, but here, like I think you do, you are the one that is that thinks yourself is standing still. So to answer Josephine's question, these numbers that I just wrote at the bottom of the page here, the 50 and the 40, those are both from the perspective of object C, which is you. So the 50 number that Josephine asked about, her explanation for it is exactly right. That 50 number is how fast bolt A is going according to perspective C, which is you, or is the lab, or is planet Earth. But I'm going to stop for a second because it's so good. Wait, let me literally ask Josephine, does that make, like, am I answering your...
Yeah, that does make sense. So like the third object is you, because you are the one that's throwing the bolts.
Oh, I say
or like viewing them being thrown.
viewing, right? Viewing.
Okay.
Yes, very good. And no, that's awesome. That's awesome. And to everybody, the reason I just suddenly use the word you, I'm not saying it's always like you, but the reason I'm using the word you is because I just reread the problem to be careful and to be clear. And the problem introduces the numbers as saying you view, blah, 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 blah. So that's why, right. So yes, you're the one viewing it. You're the one watching it, observing it, measuring it. So you are that third perspective. Yeah.
I just had a quick other question.
Oh, yeah.
I'm not sure if you're like, I'm sure you'll probably mention it at some point, but part of the reason that this question tripped me up a bunch is just the way that it was worded in the beginning, like at the beginning of the third question. It makes it almost sound like bolt B is like thrust down into the hole, and I guess I kind of got confused as to whether or not that affected its velocity, or if that was like a negligible
Oh, wait.
component.
No, wait, that's another great question. No, you're totally right. It is important. No, you are reading it correctly. The question absolutely does say that the second bolt was thrust down. Right. No, that is important, as opposed to the first bolt. Bolt A is just dropped. So drop means it comes out of your hand with no velocity at all. It has an initial velocity of 0, like bolt A does. But you're absolutely right. Bolt B, it says it's thrust. So what does that mean? It means it comes out of your hand with some non-zero velocity. It means it's thrown. It, like, from the minute it comes out of your hand, it's already going at some high speed. And in this case, the high speed that they tell you is 40 meters per second. So the thrust word is the English word that like allows for that 40 to be true.
Oh, okay. I wasn't sure if like it was going, I don't know, that was maybe a silly question. Maybe it wasn't, but it was like I wasn't sure if it was already going 40 like meters per second, and then that thrust was somehow affecting that. But that makes sense, that explanation. Thank you.
Okay, yeah, no problem. And it's not, guys, or everybody, that is so not a silly question. It's really not a silly question for 1,000 reasons. That particular thing. So let me back up for a second, because I'm just so glad Josephine, I really think that Josephine is talking for a number of people who have these concerns also. And I know from experience, there's people in the room that don't even know they were confused by that. Like really, like for Joe, like, but they were, or they are, or that, whatever. So first of all, it's super common. We're getting used to this. It is super common for everybody in physics to be confused about this whole idea that something could be going already at the beginning of an experiment. It really does confuse a lot of people. So let's pause for a second. Like at the beginning of an experiment, like when you throw something or you shoot a bullet out of a gun or something like that, we often say there's an initial velocity. Like we'll say a bullet comes out of a gun with an initial velocity of 200 meters per second, or a pitcher throws a ball, or a volleyball person, like whatever, I forget the word, sets, I don't even remember, like punches, what is that even? Whatever, hits the ball. And from the moment it comes out of their hand, we'll say the ball's already going at 20 meters per second. And that totally confuses a lot of people until they get used to it. A lot of people legitimately think, wait a second, like when a bullet comes out of a gun, like doesn't it have to start at zero? Like, isn't it first at zero because it was sitting at the gun? And then or when you throw something, isn't it necessarily first zero and then other things? And here's what we're saying. If you throw something or you fire something out of a gun, when the bullet is sitting in the chamber of the gun, when it's just sitting there, yes, its velocity is zero. But the whole point of a gun is that the gun accelerates the bullet up from zero when it's sitting in the back of the gun, up from zero, up like really quickly. It accelerates it up to some speed so that by the time the bullet even comes out of the gun, it's already going. Like that's the purpose of the gun. Or when you throw something, sure, when the thing is sitting in your hand, it's sitting there, but you move your hand, you bring your hand back and you move it so that on purpose, so that by the time the ball leaves your hand, it leaves with a high speed. That's why you shoved your hand in the way that you did. By the time it leaves your hand, by the time it's no longer in contact, it already has a high speed. If it didn't, then it would just dribble out of your hand and fall to the ground. So this is why we'll often distinguish between dropping something from rest, which is bolt A. Bolt A just literally got dropped. I just released it from my hand. So it came out of my hand with no speed at all. But the other one I threw, like I shoved my hand down, I thrust it so that by the time the other one came out of my hand, it already had speed like this. And that's what we call initial velocity. And that does take getting used to. Josephine is definitely not crazy at all. But what if you see what I'm saying, once you get used to it, then this is going to happen all the time, that objects can start from rest. That means from the moment they are already not in contact with whatever originally propelled them, then they have some velocity. I don't know if that's clarifying, but that's definitely. But the other thing I would just want to say, and then I will move on. Josephine said a very common classic thing just now, and I'm really so glad that she did, if I haven't made that clear already. Like she said, like she's like ready to do the problem, right? You could tell by her attitude and by what she's like ready to go. She's ready to do the math. She's like following the instructions. But she got tripped up by the wording, right? Very common. What I want to say to all of you is, oh yes, the wording is a big part of physics. Like this is why it's not just pure math. It is physics. The wording is it, but both how we word the questions and how you word your responses is a huge part of it. Now, I'll tell you this, I am not perfect with the English language at all. So, and sometimes I'm confusing for sure, but I tell you this, we are not trying to confuse you with words. We're trying to use words that get at all the concepts that we need to, that the pure numbers do not express. In other words, what I'm saying is the words are a huge part of it and they do take getting used to, but you do have to take the words really seriously. Like we use words maybe in a slightly different way from what you're used to, so you get used to them. But always assume when you're looking at the words, assume that every word is meant to matter somehow, and every word is intentional. I'm not perfect, they're not perfect, but they're not there to trick you on purpose, definitely not. And they're also not there by accident. The words matter as much as the numbers, and it does, and it's a big part of physics, and it takes everybody getting used to. But that, anyway, whatever. So, but don't think, if you're like, wait, the word is like screaming at, don't think like, oh, I understand it all, but like, except for if only he had worded it differently, then I would get it. Well, if I had worded it differently, it really might be a different question. Start with the assumption that the words actually are trying to do something. Anyway, you get my point. But no, that's a great question. Okay, wait. Right. Okay, so I'm seeing in the chat. Yeah. But you gotta, really what this class is, it's a class in translation. We're trying to teach ourselves how to translate from the math into English and how to translate from English into math. That is a big part of what physics is. I'm not saying, it's not a joke. And I'm not saying you're wrong to be confused, but I am saying it's not an accident, and it's not just you, or it's not just like a detail. Like, it is the issue of the class, for whatever it's worth. So that's why all these questions are good. But okay. Back to the thing. I know where I'm taking. So I have these two facts. According to the way the problem was described, I believe bolt A is at T. I'm just looking at the first moment, just as an example. At the fifth moment, just as an example. For example, I'm looking at the fifth moment. At that moment, bolt A is going 50 meters per second, according to me, according to the guy standing in the garden, and volt, i.e. according to object C. And bolt B is going 40 meters per second, according to me, according to the guy in the garden. So to answer this question finally, what that means, when the question asked, so if we're asked, what is bolt A? What is velocity of bolt A relative to bolt B? What we're really being asked is, we're being asked, what is VAB? Like, that's what VAB means. Bolt A according to bolt B. And in this case, what we're saying is VAB equals VAC minus VBC. In other words, VAB is 50 meters per second minus 40 meters per second, which equals 10 meters per second. Okay, this is just, this gives me 1 point on the graph. In effect, obviously, I'm going to go back and translate this to the graph in a second. But I'm saying VAB equals 10 meters per second. In English, I'm saying if bolt B were to look up or look down and see what bolt A is doing, if bolt B is like a car on the highway and it's looking at this other car ahead of it, it sees the other bolt ahead of it going 10 meters per second faster than it. Like, how much fast is A relative to B? We're asking how much faster is A going than B. So we're asking, if you were B playing this video game, like we were given fact according to some dude, some dudette, you standing in the garden watching these two bolts. But now we're asking you to shift your perspective and look at what's happening from the perspective of bolt B. And what bolt B sees, observes, views, measures is bolt A going 10 meters per second compared to it. If bolt B views itself as at rest, which it does from its perspective on the world, it sees bolt A going 10 meters per second compared to it. And again, that's not an illusion. And that's not a mistake on bolt B's part. That is bolt B's perspective. Your perspective, you see bolt A going 50. B's perspective, it sees bolt A going 10. You're both right. You're both equally wrong. Neither one of you is more correct than the other. These are just two perspectives on the world. So VAB equals 10 meters per second at T equals 5. Now, that was just an example of a point. If I take that logic, I can make the whole graph. So the graph, just to answer this question, the graph Now remember, in my frame of reference, we started last week, I'm calling anything that goes down positive. All my numbers are positive because everything's going down. So if this is time measured in seconds, and on the vertical axis is VAB, right? That's what the vertical axis is, according to this question. The velocity of A relative to B, as measured in meters per second. Well, at time equals 5, at time equals 5, the velocity is 10. I'm sorry. Sorry. At time equals 5, the velocity equals, so let me draw this a little bit more to scale. You see what so what I'm doing is I'm drawing a straight line, and I can go and it's 0. Well, yeah, I'm drawing a straight line. I'm starting at t equals 5 because both we had to wait until t equals 5 for both for the problem to start, for both bolts to be in motion. But once both bolts were in motion, then from then on, bolt A was always going 10 meters per second. Hang on, I'm sorry. Whoa. I'm sorry, that is not right. I'm sorry. The first point is right. The first point is what we figured out a second ago. But from then on, I'm sorry, it goes like this. This is the graph. And we should pause for a second because I just made a mistake. The graph is a horizontal line. And why am I saying that? The first point that we just figured out was at t equals 5, VAB equals 10 meters per second. It's going 10, in other words, A is going 10 meters per second faster than B. But the next second at t equals 6, if we do this again, if we do another second, if we say VAB equals VAC minus VBC, at t equals 6, VAC equals 60 meters per second, and VBC equals 50 meters per second, right? And this goes back to Josephine's thing, the thing that she very correctly said at the beginning. We are told that we're watching these bolts, and each one of the bolts gains 10 meters per second every second. Each bolt is in free fall. Each bolt is accelerating at a constant rate. So when A gains 10 meters per second, so does B. So the difference between the two of them, the difference in velocity between the two is always 10 meters per second. One is always going faster than the other by 10 meters per second. So the answer to this problem is a horizontal line. I'm going to pause for a second and I'm just going to ask, can you raise your, wait. Oh, great. Oh, some people are putting in the direct chat. Hold on a second. And if you put something in the direct chat, that definitely counts as participation. You should definitely, because it is helping me, you should definitely submit for points. Oh, 2P. Okay. Thank you. Those of you in the direct chat who are saying things about this, that's very helpful to me. Thank you. Well, I'm just, okay, cool. All right. So I'm assuming, then I've got a bunch of feedback. Thank you. So maybe this is redundant, but like, just raise your electronic hand if this is clear, like now, or sort of. Well, sort of. Okay. So maybe I should do raising. Okay, cool. Thank you, guys. All right, awesome. Okay, and it is true. Okay, great. And by the way,
I can't raise my hand, but I'm letting you know I hear you.
Okay, great. You can't. Okay, thank you. I appreciate it. Awesome. And look, honestly, I'll move on, but you could see how like excited and loud and everything I'm getting. I want you to know that I know like this isn't complicated mathematically, but it is hard conceptually. And honestly, this is the heart of physics. Like, I am not expecting anybody to get this overnight. What I am telling you is that this threat, if you sort of get it, if you feel like you didn't, there was something you sort of saw before, but now you see it a little bit more, if you're even progressing and getting this comparative velocity thing, this is the thread of physics that runs through everything. That's why we're dwelling on it. That's why like we had the train of thought problem. Like, honestly, everybody thinks that what makes physics hard is the math, and it turns out the math is not what makes physics hard. The math is what people rely on to get through physics. What makes physics hard is the concepts, and the concepts are not complicated, and there aren't many of them. They're fundamental, they're simple, but they're a little bit of, and they're exactly the concepts that you use. The bottom line, I will move on now. But if you're like thinking about this, or if something's going on, this is not a trivial, this is not like some sidebar thing. This is the thing. And the ultimate thing of this that it becomes more and more mathematical, but the ultimate thing that we're really saying is whatever suspension or trick you do with your brain when you play a video game, or when you watch a movie, or when you're driving in a car and you like experience things rushing by you rather than experiencing you rushing by things, what we're here to say is that is not a trick, and that is not silliness, and that is not something that's just in your head. That is the actual way to do physics, to realize that we do that all the time. And when we do it, we're doing something legitimate. The mistake is to think that anything has an actual, absolute, true velocity through space. No, velocity is always a comparison. And we can't come up with a velocity until we choose the basis of comparison. That's what we're saying. Okay, but I know we only have 8 minutes. I know we have a lot, and I'm not assigning any new homework. Okay, like many of you still have to do homework 7. Some of you still have to do homework 6. We're just going to keep going like this until we're caught up with ourselves. Should do, but anyway, so I'm going to go to the next. I know we have 8 minutes, so I'm just going to keep going. Well, hold on. Let me just look at what we can do in 7 minutes. Okay. For right now, and make a note of this, the next problem on the homework is 4, and it's called a velocity time graph. For most of these, they're just being asked to do the graphs like from your perspective, from the perspective of the lab. So honestly, most people that did these graphs got them right. I'm not about to change your view on what you did here. Okay, so we can go back, but we just did a graph. We can go back and review these graphs like next time if anybody asks. But what I want to get straight to now, what I can do in 7 minutes, is I want to do at least one entry in this table, because I think the table is really important. So this is now I'm shifting gears. So let's, for now, skip to the table, part E. Okay. And I know we only have 6 minutes left, so I'm just going to do one entry, but I want to talk about the first entry of it.
Are we going to continue going over this homework next time we have class?
Yes. Yes.
Okay.
And then we will get to 7. Yes. I mean, and yes, absolutely. I'm not promising, like, you might have to remind me if I skip certain exercises, like right now I am. If you want me to go back to them, you can remind me and I will. But I am, yes. For example, the big old duck, the big problem at the end, we're definitely talking about before we move on to 7. I promise you that. So yeah, I mean, so the answer is yes. And again, I'm not going to assign anything new for a little while. So yes. So yeah, who was that, by the way? I'm sorry. I didn't see, who just asked that? I'm sorry.
It was me.
Oh, Josephine. Okay, great. Yes. Okay, awesome. You should submit for tons and tons of points today. Okay. So where am I? Okay. So I just want to do the first entry in this table. There's different ways of doing it. And the truth is that a lot of you actually got the entries in this table correct, which I'm happy, but I am pleasantly surprised. But I'm not sure how you got them. So let's make sure we're getting them the right way. Or there's different ways, but a right way. So like, here's the givens, right? We've got this object called Edna, and it starts at a velocity of 12. Like, so it was either like shot out of a gun or it was thrown, like a baseball or something like that, when it starts with a velocity of 12. And it's got a constant acceleration every moment of -4 meters per second squared. So every second. So every second it's losing 4 meters per second of velocity. And right at the beginning, it hasn't gone anywhere yet. Like, so, okay. And I want to know, at least for right now, in the 4 minutes that we have left, what I want to know is what's happening to it after 1 second of motion. Okay. So I'm just going to fill in the first row of this chart. Okay. So what the givens are V naught equals 12 meters per second. X naught equals 0. These are all the givens. And A is a constant. A is always the same thing, and it's -4 meters per second squared. So here, so I'm going to the next page. Okay, so I'll just so we want to know at t equals 1, like what's V, what's A, and what's X, right? That's the question of the first row of the table. First row of table. Well, A, I'm going to go out of order, okay? I'm going to, on purpose, A, I know what A is necessarily because I was told that A is a constant. A never changes. A is always the same, so it's -4, okay? We're told that. This is an example of constant acceleration. So every second, this thing loses 4 meters per second of velocity. So from that, in my head, I can figure out what V is at t equals 1. I'm going to say in my head, I believe I can figure out that at t equals 1, V is going to be +8 meters per second. Now, how I did that in my head, I'm using logic. I'm just subtracting 4 from 12. But if you want to see it in an equation way or whatever, like how did I actually do it? The GDP that I'm using is the definition, like, so why? Well, and I'm doing the steps out of order right now just because I'm rushing because there's only 2 minutes left. I just want to make this clear. But the definition of average velocity is change. The definition of average acceleration is change in velocity per time. That is a GDP. That's always true. That's the definition of acceleration. So I can rearrange that. So I'll just rewrite that. If average acceleration always equals change in velocity per time, and here I'm looking for a final velocity. I know the initial velocity was given as 12, but I'm looking for the final velocity. So I'm rearranging it. I'm really saying this. I'm multiplying both sides by t and adding V naught to both sides and saying, well, therefore V at t equals 1 equals -4 meters per second squared times 1 second plus the initial velocity of 12 meters per second, right? That's really what I was doing in my head, is that equation. So I got 8 meters per second, okay? But now, the real issue, and we only have 1 minute left, the real hard part is how far did it get in this 1 second? Well, because we only have 1 minute left, I'll cut to the chase and say the answer, certainly. The answer of how far it got in this 1 second is 10 meters. Now, where did I get that? Where did I get 10 meters? Well, where I got it is the most important GDP, the first GDP we ever learned, that average velocity equals displacement over time, and our initial position was 0. So displacement equals average velocity times time. Displacement, how far it got. I know it's 1:30. I'm going to wrap this up in like one sentence. How far it got is how fast on average it's going for a full second. But so average, was I ever given averages here? No, I was given instantaneous velocities. What I have to do here is say, like, I have to say what I'm just about done. What is the average? I don't know. but I know since the acceleration is a constant, then the average velocity does equal the average of velocities, right? When and only when acceleration is a constant, then the average velocity, double equal sign, the mean turns out to be the median. In other words, the average velocity is 12 plus 8 divided by 2, the average velocity for this 1 second, for the first second. The average velocity is 10 meters per second. So this thing goes at an average velocity of 10 meters per second for 1 second. It travels 10 meters. It's really important to see that I didn't plug in 12 as the velocity or 8. I plugged in 10 as the average velocity. You could also use that 1FAT squared equation. We'll review that next time, but that's the end of class. You've been very patient and asked really good questions. I really appreciate it. We'll just keep going with this next time, which is tomorrow. Right. So I have to, yes, have a great day. Thank you. I'm going to run now. Thank you. Have a great day. Text or email me if you have questions. Say, great. Have a good day.
Professor?
Yes.
Hi, I just wanted to ask when our exam was, or an estimate.
Estimate, good question. We don't know exactly. We're gonna confirm it as a group, but the estimate would be like 2 weeks from tomorrow. You'll have at least a week warning with a practice test and everything before it happens, but I would estimate 2 weeks from tomorrow. But we'll probably discuss that tomorrow and confirm. But that's
Okay, sounds good. Thank you so much, Professor.
Thank you very much. Okay, thank you.
Have a great day.
You too. Bye. Okay. Oh, great. Okay. Yes. Thank you, guys. And I'm stopping the recording. Yes. Yes. Thank you, Shawnee. Yes. Send me an email because I'm going to run right now. But thank you. And Revo, you're good. I'm stopping.